Hi, Science 10. In this video, we're going to be looking at atoms, ions, and isotopes. Now, we've already been looking at the structure of the atom and talked about ions, but we're going to really focus and make sure you understand what atoms are, what ions are, what isotopes are. We're going to be doing an assignment also inside of this video lesson, so make sure you got your calculator, you've got your periodic table. This assignment will also be in Moodle, and of course, you're going to want to take notes as you're watching all of these videos. Make sure you're using pause as we go through some of the key concepts. But yeah, let's get underway. You can see an atom and an ion, and ions in solution, they'll conduct electricity, and isotopes are actually used for medical imaging, and so they're super important. Of course, we've got the periodic table right here with not only the atoms, but with the charges, it tells you about the ions. But yeah, let's get underway. Let me share my screen. Here we go. So yeah, in the assignments for Moodle, I should have done the welcome assignment, the atoms, elements, and bonds. And once you complete this video, you'll be ready for protons, electrons, and neutrons, and isotopes, and regular atoms. You'll be able to complete that one as well. In the textbook, we're in section 1.2, 1.3, actually 1.1 as well. So those are where you're going to be wanting to read. And of course, make sure to be reading our note package first. That's your main focus. It's got everything you need. Yeah, so this video, we're going to make sure we know the structure of the atom, what an ion is. Well, right here, we can see ions in action. A solution that doesn't have any ions, so this could be distilled water, or actually if you dissolve sugar in water, it won't conduct electricity. A few ions, you can see the light glows, but you get a lot, and it'll really conduct electricity well. This is probably just some salt, some sodium chloride dissolved into the water. And when sodium chloride dissolves, the sodium ion comes apart from the chloride ion. The sodium ion is positive, the chloride ion is negative, and it conducts electricity, that solution. Here we see isotopes. An isotope is an atom as well, and it's just got more neutrons. It makes it slightly radioactive. We use them in medical imaging. So if someone, particularly cancer patients, might need some detailed medical imaging, so we'll put in some medical isotopes into the person, and this would be a PET scan showing the internal organs really well and able to show up tumors and other growths inside of a person. Also, we'll look at nuclear notation. This is carbon-12. And of course, carbon is good old number 6 on your periodic table, or it has 6 protons. So that's going to be the mass. Oh, okay, so 6 protons, 6 neutrons. Okay, so that's where the 12 came from. But yeah, we'll be looking at that. There's a few other forms of carbon, different isotopes, carbon-13. Carbon-14, which is really cool. We'll be looking at that one as well. So yeah, let's just do a real quick bit of notes here on this page. And again, in your notebook, definitely be pausing if I'm going too quick and going over important concepts. And I just want to get my marker working. There it is. It takes a moment sometimes. First of all, ions in a solution. So this is something that you might be familiar with. I mean, certainly we're all familiar with electricity. Conduct electricity. Our body actually uses this for thinking and for our neurons. And isotopes, they give off radiation. Now you're getting radiation from the sun, you know, if you head outside, so it's just the amount of radiation that you want to keep to a minimum. Isotopes give off radiation. Why is that? They have lots or sort of more neutrons than they can really hold in their nucleus in the atom. Because remember, an atom has a nucleus, you know, the center. And with an isotope, it's got a few more neutrons, and it can't really hold those, and it gives them off. And we use this for medical imaging. Okay, that's a quick introduction to some two key things we're going to be looking at. Of course, let's start with the structure of the atom. Let's start there. Okay, so there's three different subatomic particles. Now, we've looked at this already, that, atoms are made up of protons that are positively charged, electrons that are negatively charged, and neutrons that are neutral. Let's do a model. On your periodic table, find fluorine. Again, pause the video right now, just find fluorine. What you're going to notice, press play, get me going again here. Fluorine is number 9, and you'll notice a 19 down here. That's the mass, right? And of course, neutrons plus protons gives you the mass. And the number 9 here is the proton number, or we call it the atomic number. I like to call it the proton number. This is your number of protons. Let's do a model here of the fluorine atom. And all of this information is on your periodic table, right? You can use your periodic table, these numbers, to draw a model of the fluorine atom. Once you've got that model, you'll actually be able to use it to predict whether fluorine is it chemically active? It certainly is, but the model will help show you that. And also you can figure out, if it's an isotope, how many neutrons it's got. For example, if it's kind of the normal atom, or is it one of the isotopes of fluorine? But yeah, let's make a model here. Let's start in the center. We'll just put an F so we know we're talking about fluorine. Let's put how many protons there are. So take a look. So 9. And let's put a little p for protons. How many neutrons is that? That's our mass. So subtract the protons. And we're going to get our neutrons, right? Well, 19 minus 9, so there's 10 neutrons. You might not need a calculator for some of this, but definitely have a calculator handy. I'm going to put a little circle because that's where the protons and neutrons are. They're in the nucleus of the atom. That's where the mass is. Now the electrons, they're found in energy levels, or also shells. You'll often hear it referred to as, or you might also hear it referred to as orbits. And there's a very distinct pattern. I mean, imagine that. There's patterns in nature. We all know this. Here is the pattern in nature. If there can be 2 electrons, there will be 2 electrons in the first orbit. Oh, that's interesting. Okay, because remember how many electrons fluorine has? Well, it's got the same number of electrons as protons, right? Let's just quickly check this here. So in terms of protons for fluorine, it's got 9. Neutrons, now we did calculate that, right? 19, the mass minus the protons. Oh yeah, so 10. And make sure you know how I got that 10, because you're going to need to answer questions on this. And the electrons, it's an atom. Remember, atoms are electrically neutral. If protons are all positive, if we have 9 positives to make it electrically neutral, we need 9 negatives because electrons are negative. Oh yeah, that makes sense. Okay, so here, remember that pattern I was just talking about with where the electrons are. They're in an orbit outside of the nucleus. If 2 of them can go in the first orbit, 2 of them will. No more than 2. And if it only has 1, only 1 will go there. Of course, fluorine's got 9 electrons to deal with. The next orbit can have up to 8 electrons. Of course, it only is going to have 7, right? Because 2 plus 7 is 9. So it doesn't quite have the full number of electrons. It's not fully stable. We're going to be looking at this. We're going to draw some more atom models, but just take a note. Fluorine is not fully stable. Its valence its outside electron, right, is not stable because it should have, and this is really cool, again, there's patterns in nature, to be stable. Well, the first orbit would have 2 electrons. Okay, so far, fluorine, the first orbit's okay. Well, there's more electrons though. The second orbit to be stable would have 8 electrons. Oh, that is so cool. And fluorine doesn't have that. And this is actually why fluorine wants to take 1 electron. Remember how we've learned that the non-metals, and fluorine is indeed a non-metal on your periodic table. Where it is, it's on the right of the staircase, good old number 9. And you know that charge, you can see it on there, -1. And that's the reason. And this is just a pattern in nature. That nature wants, if there can be 2 electrons and no more in the first orbit, and nature wants 8 if there can be electrons in the second orbit. If there's not enough, it means it's not stable, and fluorine is definitely not stable. It's in group 17. You'll notice that as well on your periodic table. They're highly reactive, violent. Fluorine, you're so violent. So fluorine will take 1 electron and it will form an ion. So let's look at ions. If it takes 1 electron, it will form an ion, because an ion is an atom that has either lost or gained an electron. In this case, it gains. Forms an ion when it gains 1 electron. All right, so let's look at that. We're going to pull up our next slide here. We're going to look at ions. We just looked at fluorine, but let's look in detail at ions. Pull up our next slide. All right, so quick little model of our periodic table. I don't have the whole thing here, but the metals are on this side, right? And this is, of course, not all the metals. It's just a few of them. Hydrogen's kind of unique. We'll talk about it a little later. It happens to be over here, but it's not a metal itself. It's a gas, unless it's at the center of Jupiter, and then it actually turns into a metal because it's under such high pressure, but that's another story. So these metals here, they give away electrons. That's their charge right there, showing you how many electrons. On the right side of the staircase, we have our non-metals, and they take electrons. And an ion, say it, write it down again. It doesn't hurt to write this stuff down again. Is an atom. It is an atom for sure, but it has either lost, and who is that loses them, right? Put her right in there. Yep. Or gained. And again, which ones gain? You can see their negative charge. And specifically, it's about those electrons. And the reason is, ... to stabilize their valence, the valence electrons. All right, so why is that? Why is that? And again, if you have to pause, and definitely you might want to be pausing and make sure you're getting this key information down. You absolutely have to be writing this down. It is the best way to learn, is to be writing information down. So pause the video as you need to. But why does this happen? Here's why. To get a stable valence, again, it's that outside, those outside electrons, to get a stable valence like the noble gases. Oh yeah, we've read about that, right, in the course notes. The noble gases, they don't react. They do not react. So helium, neon, and the ones underneath here, I've just got the first three. Noble gases, and you might want this also on your periodic table, but definitely in your notes, do not react. Their valence is stable. And it actually follows that pattern that I was just talking about, where your first orbit has 2 electrons, no more and no less, as long as the element has that many electrons to deal with. And when we make some of these models, you'll see what we mean, but it's good to write this down. Again, it would be stable if in the second orbit, or the second energy level for the electrons, if there's 8. 2 plus 8 is 10. Oh, 10 electrons. Oh, that's neon. Neon's perfectly stable. 2, 8, and 8. 2, 8, 8. That's a really key pattern in nature for valence electrons. And call 288 for stability. Call 288 for stability. Indeed, this is 2 electrons plus 8, so that's 10 plus another 8, 18. That's argon. That's what argon is. Argon is perfectly stable. Oh, you're perfect, argon. Yeah, I know. Okay, that was argon talking. Our periodic table is made up of periods. They run from left to right, or horizontally. Groups, you might have already figured out. I've been talking about those. Groups run up and down. So this is group 1. This is group 18, the noble gases, group 17. Okay, so up and down, but periods, let's talk about periods and these patterns in the periodic table telling you which things are reactive, which things aren't, how reactive they are. So period 1, again, running across, and on your periodic table it'll be the same as this small little model here, because I cut out part of the periodic table just so you can see it on the slide, does just have hydrogen and helium. So period 1, to be stable in the valence, should have 2 electrons. And definitely write this down, but also be thinking about this. So stable electrons in the valence would be 2. Okay, interesting. Period 2 on the periodic table, the table of patterns. So period 2, lithium, beryllium, boron, carbon, etc. goes all the way across to be stable. So the stable electrons in the valence would be 8. Now the only ones that are stable, helium, neon. Helium has exactly 2 electrons out in its first valence and its first energy. Well, its first and only valence, its first energy shell, its first orbit for electrons. Neon does have 2 orbits for its electrons, and you'll see that when we draw a model of these. And in its outside, or its valence, it's got 8 electrons, so it's perfectly stable. Period 3, you're gonna start to pick up some of the patterns here, but write this down. So stable electrons in the valence is also 8. Oh, that's cool. Cool patterns. Neat, neat, neat. Let's draw some models. Let's draw an atom model for hydrogen. So hydrogen, we'll put right at the center. Well, it's only got 1 proton. That's it. It's very small. Super light, super powerful, actually. And therefore 1 electron. Not stable. Oh yeah, exactly. Hydrogen's not stable. What about helium? Let's compare it to helium. Helium's got 2 protons. And because its mass is 4, 2 neutrons. Remember that number 4 there, we got to add up the proton and neutron to get the 4. You know, pause the video right now just to see what I'm talking about. 2 protons, 2 neutrons. There's our mass, right? All right, if I got 2 protons, therefore I got 2 electrons. Oh, there we go, just 2. Perfectly stable. Let's keep going. Let's do lithium. Again, have your periodic table right beside you so you can see. I just scrolled down so you can't quite see mine. So lithium's got 3 protons. As you can see, it's element number 3. Look at its mass is 7. Well, it rounds to 7, right? And so therefore there's 4 neutrons because 3 plus 4 is 7. Let's draw a circle to show our nucleus. So we're doing an atom model. Now, there has to be 2 electrons in the first orbit. If we have 2 electrons, we definitely have 2. We actually have 3, right? So we can put 2 there. We can't put all 3 though. So 1 more out here. Oh, that's not stable. Oh, wow. Yeah, there should be 8 there. Oh, it probably gives that electron away. Yeah, it does. It's good old neon. Let's go over here to the noble gas neon. Again, look on your periodic table, find neon, and if you have to pause, pause right now and try to draw the model for neon. Hit pause and see what you can do, and then press play and see what I did. Okay, 10 protons. You'll see the mass of neon is 20, so therefore 10 neutrons. Let's draw a circle. There's the nucleus, there's all the mass. There's all the mass. We've got to draw the electrons in their orbits out here. If we can put 2, which we can, we'll put 2 there. Because 10 protons, we got 10 electrons to deal with. So we can put 2 here, we can put 8 there. Again, that's the rule, that's the pattern. There's only space for 2 in the first orbit. There's only space for 8. If you've got 8, neon happens to have 8. Perfectly stable. Lithium is not stable. It doesn't have anywhere near 8. This is why lithium loses 1 electron. Okay, let's do sodium. Do a model for sodium. I'm going to do it, but press pause and draw your model for sodium. Get how many protons, get how many neutrons. Okay, so as you can see, it's got 11 protons and it's got 12 neutrons, right? It's got to add up to 23 because, you know, you round to the nearest whole number. All right, let's put our electrons in their orbits. If we got 11 protons, we know that we've got 11 electrons. Now we can't put all 11 right here, only 2. There's only space for 2. We have to put 2 there. If we have 2, we definitely have 2 electrons, right? We've got 11 of them. So what's next? Well, let's put 8 electrons because the second orbit holds only exactly 8 if we've got them. 2 plus 8 is 10. We got 1 more. Oh, that's why it loses its electron. It's not stable because compare this to argon. Do the model for the argon atom. Go ahead, press pause, draw yours, then press play. Okay, let's look at it. 18 protons, right? 22 neutrons. Let's draw the circle. Again, you just use your periodic table for this. You can see argon on your periodic table. Got mine right here. So yeah, let's do our electrons. There's 18 protons, therefore there's 18 electrons. So there's going to be 2 here. There's going to be 8 there. So now so far we've got 10, and there's going to be 8 more, and it's perfectly stable. But sodium is not. So these are all metals here. They give their electrons away. You know, the lithium and the sodium. Let's draw a non-metal. Let's do chlorine. Look at your chlorine on your periodic table. Do the model for the chlorine atom. I'm going to do it right underneath here. I just moved this over a little bit. Do that model for the chlorine atom. Press pause, and then you can take a look at what I create. All right, so let's do that chlorine atom. We'll put the Cl, its symbol. How many protons? We've got 17 protons. How many neutrons? 18, because it's got to add up to 35, right? We round that to the nearest whole. You can see it's 35.45, but you just round it down. Some of them we round up, some of them we round down. Just follow your normal rounding rules. Okay, 17 protons. Therefore, I've got 17 electrons to deal with. I've got to seat them. I've got to put them in their orbits. 2 in the first. Yeah. 8 in the second. Cool. 7. Oh, not quite right. Unstable. Unstable. Actually, let's line this up a little differently with sodium. If I just had to draw on this like that, see, chlorine is missing 1, and sodium has 1 to give. If we put those two together, this is why they bond right there. When that 1 plus 7, right? And so we'll just change that right there. They end up, and it's actually the chlorine actually takes that, right? Takes that extra electron, and the sodium has lost an electron. So if they get dissolved in solution, so if we dissolve that salt, your sodium ions will come out. They'll be +1 AQ, and the chloride ions will come out Cl -1 AQ. AQ means aqueous. It's dissolved in water. If you think about it, we've got 11 positive protons, right? Because think about what's happened here. Let's just pull these apart. That sodium gave away an electron to the chlorine, which we now call chloride. Just didn't want to cut my little Argon model there. Okay, let me just use my mouse. There we go. All right. So think about what, remember, we know protons are positive. So we got 11 positives, but now we only have 10 negatives, right? Put those two together mathematically, that's where your +1 comes from, right? Put that in a calculator. 11 and then add -10, or just subtract 10, you get +1. Here, with the chlorine, we've got 17 protons, so 17 positives. But now we have 16, we have 18 negatives, because electrons are negatives, right? Okay, I give you $17, but then I take 18 because, you know, you actually owe me 18, right? Well, you're -1, basically, because, yeah, you don't have enough money, right? So you tell me, oh, I'm going to have to owe you, right? And again, do it on a calculator. 17 minus 18, you're going to get -1. That's an ion. They are atoms. They are atoms that have either lost or gained electrons. The periodic table shows you all of the ions. Let's look at all of those ions together. I'm just going to flip to that page on my notes. There we go. Okay, so let's go here. Here's our periodic table. So your periodic table needs to absolutely be in front of you, but take a look at this one as well as looking at yours. You'll notice all of the metals, they've got a positive charge. So it's showing you that when lithium does form an ion, it is Li + 1. So for example, lithium, its ion would be Li + 1. That would be the ion. And let's say it's dissolved in solution. And definitely you could find that in the oceans, or in probably even in rainwater and in creek water, etc. The lithium atom, well, you know something about it as well from the periodic table. All metals are monatomic, and all metals are solid, well, except for mercury. Li, solid. No charge. Atoms have no charge. Atoms have no charge. They're electrically neutral, right? But this ion would be just like how you just saw how sodium lost an electron. Same here with lithium. To become an ion, it's going to lose. It's going to lose. You're going to lose. What about oxygen here? The oxygen ion. Oh, -2, AQ. Be pretty rare to actually find it. That's kind of a rare one. Let's do one that's a little more common. Fluoride Ion. Versus the fluorine atom, which actually is diatomic, F2 gas. So it has to be fully balanced, to basically balance off its valence electrons. That's what it does. Oxygen is also quite unstable, so it makes itself into an O2. So this is rather interesting. In fact, all of oxygen is O2. Nitrogen, here's its charge, right? Nitrogen ion, AQ. Nitrogen as an atom doesn't exist individually as atoms. It exists as diatomic gas. Again, nice and electrically neutral as well. So yeah, all of this information now you know is on your periodic table. You know the atoms are here, and if you look at the charge, the ions are here. We're going to look at isotopes. We've looked at ions. Ions, again, are atoms that have lost or gained electrons. Isotopes have a different number of neutrons. So let's look at isotopes. We're going to look at a specific one here first. We're first going to talk about the beryllium atom. This is beryllium. It's on your periodic table, number 4. And so it's a metal, so looks like most metals, kind of a shiny substance. There also can be isotopes of beryllium actually made in the upper atmosphere. This is really, really cool. When we get cosmic rays from space, you'll get different isotopes of beryllium created. One of them will be beryllium 7, but this here is beryllium. This is a model of beryllium, and just make sure this is a model of beryllium. Look at this carefully. There's your protons with their charge. There's your neutrons, they have no charge. Is that the model for beryllium? So just do a double check. Yeah, that's definitely the model for beryllium. Let's make a model for beryllium ourselves. So put your number of protons. I'll catch up to you in a second. And put your number of neutrons. Our mass is 9, so therefore our neutrons are 5. Let's draw a circle. Let's do our electrons. Might as well finish this off. It's got 4 protons, got 4 electrons, 2 there, only 2 here. So this is also why it loses those 2, but we're interested in neutrons now because we're talking about isotopes. So yeah, we were just looking at ions, so that's kind of cool. But let's talk about isotopes. There's this is actually beryllium 9 right here. So the normal beryllium atom is called beryllium 9 because there's its mass. And here's the notation that you need to write for beryllium 9. So definitely write this down. Be, put a 9 here, and put a 4 there. Well, that's interesting. So what does the 9 represent? Well, that's the mass of beryllium 9. Again, the most common form, the most common isotope of beryllium is that beryllium atom right there. And this, of course, 4, well, you know what that number is. That's the proton number, or the atomic number. And be comfortable with calling this number both. It's atomic number / it's the proton number. So you need to be able to read something that says beryllium 9 and then write this. You need to be able to do that. When you read this, you know how to write that right there. You're going to need your periodic table, right? That's going to help you out. Going to help you figure out. Always refer back to your periodic table. Let's talk about beryllium 7. It's actually formed in the atmosphere when really energetic cosmic rays come from space. So basically from the explosion of black holes and neutron stars, so all kinds of cool stuff that happens in space. High energy stuff happens in space. You can get high energy particles, and basically you can get something called beryllium 7 formed. Okay, Well, if that's how to write beryllium 9, now protons basically never change. Electrons with ions, of course, we just saw how electrons can get lost or you can gain them. And isotopes are about getting a different number of neutrons, but protons never change. So using your periodic table, Be, well, 7 and 4, right? Because that never changes. The proton number, so you know that. And then this one, it was in the name, and this is its mass. Oh, that's interesting. So this, if we drew this, I'm really interested now. This one has 4 protons, but instead of 5 neutrons, 4 plus, oh, interesting. This has got 3 neutrons. So it's got a different number of neutrons. It would still have all the same, you know, the 2 electrons, because those have to balance off the protons. 2 electrons there, 2 electrons there. But it's got a different number of neutrons, and that's what an isotope is. Isotopes, they are atoms. Oh, this is handy. So they are atoms with a different number of neutrons. Write that down. You want to know that. Okay, cool. So let's look at carbon. We've looked at beryllium and beryllium 7, which can form in the atmosphere from high energy particles hitting the upper atmosphere. But let's look at carbon, some of the common form of carbon, which is carbon 12, and we'll talk about a couple other isotopes of carbon. Okay, so a reminder, our atomic mass here . And yeah, maybe draw this out in your notes. So maybe quickly hit pause and just draw this right here. Okay, press play again. Here we go. So that right there is your atomic mass. And of course, this is your protons plus neutrons. Okay, yeah, that's a bit of that's a bit of review. And for carbon, it's going to be 6, therefore plus 6. Okay, yeah, 12. We round it to its nearest whole number always with this. And again, this is your periodic table shows you this. It shows you the proton number. That never changes. And atomic molar mass and neutrons can change. Yeah, wow, man. So here are 3 different forms of carbon, 3 different isotopes. This is the most common one, and we would just call this the carbon atom, right? Technically, you could call it an isotope of carbon. But, you know, we'll just make sure we're nice and consistent, and we've been calling it a periodic table of atoms, so a periodic table of the most common isotopes, most common atoms. Let's write the notation for carbon 12. So you got the name carbon 12, so we need a C, and we put a 12 up here. And remember, protons never change, so put a 6 there. Okay, so if I say carbon 13, or if you read carbon 13, do a C. What goes here? A 13. Okay, carbon 13. Protons never change. Again, look at your periodic table. Find carbon. When you look at carbon, you'll see the 6. You'll see the proton number. You'll see the 12 down here. But the main thing is that proton number never changes. Right here, this one, he says, I never change. Put a 6. Okay, what about carbon 14? I'll put the 14 right there. What goes down here? Ta-da! Put that in your notes, that this one is called carbon 12, that this one is called carbon 13, and this one is called carbon 14. Cool, cool. What we want to talk about is not there. Okay, cool. A little bit about carbon-14 now. I think I wanted to show you something with carbon-14, but I'll get to that in maybe in another video. I'll just mention it. Carbon-14 is used to date the age of ancient bones and ancient dead stuff that we dig up. I think we've got that in the next video here. But yeah, let's do a little review. Yeah, actually that is on the next slide. Sorry. Let's do a little review here, what we got so far. And I think it's this one. There we go. Okay, atoms, first of all, are electrically neutral. So protons and electrons are equal. So if you're talking about the good old lithium atom, and you know lithium is, again, look on your periodic table number 3, well, you know that lithium has got its 3 protons. It would have 4 neutrons because of its mass would be 7. And those 3 protons are balanced off by 3 electrons. Again, the electrons go in a certain pattern. And, you know, again, oxygen's got 8 positive protons in its nucleus, and it must have 8 negative electrons surrounding the nucleus in its energy levels in the electron energy levels. Actually, let's draw oxygen. Let's do that. Look on our periodic table. Good old O. How many protons does it have? Check it out. 8. What's its mass? 16. Therefore, 8 neutrons. Okay, draw these circles showing you that's the nucleus. That's where all the mass is. There's going to be 2 electrons there. There has to be. There can be no more, and there can be less, but you know, oxygen's got 8, so there's not going to be less than 2. Oh, 6. Not quite enough. Not stable. That's an ion. Ions are atoms that are either lost or gained. Well, this can form an ion, right? So this right now is the oxygen atom. But if it gained 2 electrons, an oxygen ion, its model, well, it would have 8 protons, 8 neutrons. There would be 2 electrons and 8. Oh, wow. Yeah, because it would have gained 2. And it would have a charge of -2 because it gained 2 negative electrons. Oh, and then this would be stable. Relatively. In fact, the way oxygen does it is it likes to bond up with other oxygen molecules and make an O2. This is literally why we get O2, because it's trying to share electrons. Basically, it forms a bond with another oxygen atom, and it shares electrons. I share, you share, we are molecular. It's a molecular bond, and they share them. They were just singing. Those are 2 oxygen atoms singing. I just know it was beautiful. Okay, we'll talk about this guy in a moment. So that's ions. Isotopes are atoms as well. They have a different number of neutrons. So we've seen some examples. Uranium, find that one on our periodic table, number 92. Way down at the bottom of your periodic table, you'll see it sort of more the bottom left. It's got a mass of 238, so therefore it's got 146 neutrons. Yeah, let's draw this one, right? That's huge. It's a super big and massive atom, so big it gives off neutrons actually and protons as radiation. As it does, the uranium changes into other elements. It's totally cool stuff. But uranium, if you had some in your hand or whatever, is well, it's quite radioactive, so it gives off lots of radiation, lots of heat. We can use it to heat water, make steam in nuclear power plants. That's how nuclear power plants work. Another isotope, I promised I'd talk about this, carbon-14. Okay, so good old carbon-14, right there, right? That's how to write it. Mass is 14, so 6 protons, so therefore 8 neutrons, right? 6 plus 8, 14, that's where that comes from, your protons plus your neutrons, we're going to get our mass. Oh, yeah, right? So it's just a little too big. And so one of its neutrons changes into a proton and it becomes nitrogen. In doing this, it gives off a bit of radiation. It's inside of all of us, all living things. So this would have been a person maybe 2,000 or so years ago. And while they were alive, they had a consistent amount of carbon-14. It's all around us. You're taking it in all the time. This person would have taken it in all the time. But as soon as you die, you stop taking food in, water, you stop taking in carbon-14. So all of us would have a known amount of carbon-14 inside of us. You know, if we know that an average person or the weight of something when it's alive is say 70 kilograms or whatever, we know how much carbon-14 might say be about 100 grams. After 5,000 years, it decays and there's only 50 grams of it left. Where did it decay to? Oh yeah, some of it became nitrogen. So literally, this is how we figure out how old stuff is. Up to about 50,000 years, this works. And then we have to use different dating techniques. I mean, definitely you have to use a different dating technique if you're looking at someone who's 50,000 years old. But anyway, that's a joke. So that is atoms, electrically neutral, ions, which are atoms they've just lost or gained electrons, and isotopes. Think about all the examples we looked at. We're going to do some problems though now. We're going to fill out a chart together, and this is an assignment that you've got right in your Moodle course as well. So we can get you can get 100% on this turkey. Okay, so I just want to make sure I can see my periodic table. Have yours beside you, and again, your assignment literally is this exact assignment. So the atomic number is 7. Well, that's nitrogen, and so our mass number, we'll round it, 14. So don't worry about putting the number that they have, round it to its nearest whole. Number of protons is going to be 7, right? Because we go atomic number or proton number, because that's my proton number. Number of neutrons, they give it to us. Number of electrons when we're talking about atoms, so it's going to be 7, right? Those two match. Name of the element, nitrogen. Okay, this is something you need to know. N2 gas, that's what it forms. Let's do the next one. Put that on your periodic table for nitrogen. Number of protons, number 9. Let's find number 9 on our periodic table. Well, it's fluorine. Okay, so fluorine's got 10 neutrons. Yep, its mass number is 19. Right off the periodic table, right there. The atomic number for it is atomic number 9, or the proton number. Almost a trick question there. Number of electrons, 9. Hey, that's handy. Name, fluorine. F2. Got to know that. Shares its electrons. It's molecular. I share, you share, we're all molecular. Number of protons, 12. Magnesium, right? Because that's the proton number. Number of neutrons, it's going to be 12 as well. I'm going to sneeze, sorry. No, I'm not. Number of electrons, 12. Hit pause and try to do these on your own now before I do them. Magnesium. All metals are monatomic. This is just MgS. Always put the state of matter. Atomic number 20. Find atomic number 20. Find its mass. Find the number of protons. There, we already got the number of neutrons. Well, I can get the mass from those two numbers. It's 40, right? We're talking calcium. Calcium does have 20 protons. Its number of electrons. Protons equal electrons, right? So that equals that. 20. Calcium. Calcium is a metal. All metals are monatomic. Ca, solid, one atom. They're not diatomic like nitrogen and fluorine. Okay, atomic number 30. Find that. Looking for number 30 on our periodic table. Well, there's number 1, there's number 2, there's number 3. Let's find number 30. Good old zinc. What else we know about zinc? Its mass, yeah, 65. It's already got it. Number of protons, 30. 65 minus 30. Literally, right? Is what we're doing here. What's that? 35. Number of electrons, those two equal, 30. Zinc. Zinc is a metal. Monatomic, Zn. What's its state of matter? Check on your periodic table. Solid. All metals are solid. Come on, man. Okay, mass number 59. So I don't have atomic number. Oh, number of protons, 27. So proton, atomic number, and proton, that's the same thing, right? Same. So looking for number 27, therefore. There it is. Cobalt. Yeah, that's cool stuff. Good old cobalt. What do I know about cobalt? I got a mass, number of neutrons. Let's subtract these two, right? Because my mass is 59. Is that correct? Yeah, 58.93. So 59 minus 27. Said we should have a calculator, so I'm going to definitely use a calculator for this here. Okay, turn it on. Clear, clear, clear. 59 subtract 27. 32. My number of protons, atomic number, 27 for cobalt. Yep, that's 27. And number of electrons, therefore 27, right? 27, yep, cobalt. How about we write the symbol for this, of course, with its state of matter. CO, it's a metal, solid, monatomic. Mass number 16. Number of electrons, 8. Okay, number of electrons, that'll give us the number of protons, right? So which one is this? Which one has 8 electrons, has a mass of 16? It's got 8 electrons, it's got 8 protons. If it's got 8 protons, well, that's its atomic number. Oh, it's number 8. Oh, it's oxygen. Number of neutrons, 8, right? 16, oops. 16, subtract 8, the mass, subtract the proton, going to give us 8. It's oxygen. You know how to write oxygen. We all know how to write oxygen. O2, O2 gas. We now know why it's O2, because it's stabilizing its electrons. It has to share them. It forms a molecular bond. I share, you share, we're all molecular. Here we go. You can go fill out this assignment. It's in Moodle, and you'll find it right there. That's the video on atoms, which you've got on your periodic table. Ions, which are also atoms on your periodic table. You know the ions by the charge. And isotopes. So an isotope is going to have a different number of neutrons. Take care, Science 10.